Yeah. Okay. So what we are going to do today is, I told you, we are going to do something different, not very different, of course. We are going to see, okay, how the force of gravity is going to control the motion of the planets and the satellites and everything, okay, and check whether you follow me or not, okay. So I will speak slowly. If other days I've been speaking fast, please stop me, huh? Okay. Let me tell you what are we going to do today. See, we are going to talk about orbital velocity. I'll tell you what are these. Orbital speed also you can call it. Then we will call it something called time period. We'll do this is the second one. First one is this, and then third topic that we'll do. All are related based on one topic only, of course. The third thing we are going to calculate is height. Height of a satellite. And then I'll show you that you can apply this three formulas that we are going to derive in very many situations. Okay. So one by one, I'll show you what is going on. Please, if you have problems and all, please stop me. Huh? So see. Uh, First of all, let's say this is Earth. Okay. I'm doing this derivation for Earth. I told you you can apply for any case you want. No, this is Earth. Mass of the Earth is how much? We are going to take ME. Radius of the Earth, as usual, I'm going to take RE. And let's say we have a satellite. You know, right? What is a satellite, right? Something which goes round and round the Earth, right? We will call it satellite. No? So let's say this is the satellite. Okay. This satellite that I've taken right now has a mass of M. Okay. And it is orbiting Earth. I hope you understand the meaning of orbiting Earth, right? Orbiting Earth, right? It means it is moving around the Earth. So in this orbit, okay, I've drawn a very big orbit here. Let me say that the satellite is launched at a height of h. I hope you understand. From the surface. So far it is from the surface of the Earth. No, satellite cannot be very close to the Earth, right? If it is very close to the Earth, it will fall, okay? Now this satellite, of course, it cannot be stationary at that height, okay? It has to move. If the satellite is not moving, right, it is going to fall, okay? So I'm going to give it a velocity. To be in this orbit, let me tell you like this. To be in this orbit, the satellite must have a velocity called v, and that is what is called as orbital velocity, okay? The speed which is required for the satellite to be in this orbit, we call it orbital velocity, okay? Imagine I have a bigger orbit, right? The satellite, if I take it to this bigger orbit, you will notice that it will require a different amount of velocity to be in this orbit. I hope you got my point. That means at different orbits, the satellite will require different velocity, okay, to stay on the orbit, okay. So I hope you're getting me what I'm trying to say. And then finally, I'm saying uh, we are also going to talk about time period. Time period means how much time it takes for the satellite to go one round. Okay, it will start from here, take one round and come back to the same location, right? So that time taken, we will call it time period of the satellite, okay? Later, I'll show you how we can extend this idea to even planets and everything, okay? But right now, we're just talking about satellite, okay? I hope you got me what I'm trying to say, okay? Then I'm telling you right now is this, see, the satellite is going round and round because of force of the Earth. And that force is gravitational force. I'll give an example right now, and then we'll start talking about that. Let me tell you, since this satellite, right, is in a circular motion, anything which is in a circular motion, right, rotating in a circle, right, definitely must be experiencing a force called centripetal force. And that force, let me show you the direction of that force. Let me draw the satellite somewhere here again. Don't think there are two satellites, there's only one satellite. The centripetal force is always pulled, or let's say is directed towards the center of the whole circle that in which it is rotating. Okay, so this is the direction of centripetal force. If it is not clear, let me give you an example. Okay, I told you centripetal force is a force which acts whenever an object is rotating in a circle. Let me give an example. Okay, so this is, suppose this is who? This is Ryan. Okay, so this is Ryan. Ryan wants to rotate his cat. Okay, so he's going to take his cat. This is Ryan's cat. Okay, tie the cat, right? And he wants the cat to rotate like this. See, if I ask you, is the cat rotating in a circular path? Yes, the path of this cat is circular path. Okay, and the cat remains in the circular path. Okay, let me tell you, or let me ask you, Why do you think the cat remains in the circular path? If you can answer me in a very rough way also, it's fine. Why do you think the cat remains in the circular path? Or let's say, why does the cat doesn't fly somewhere here? Why does the cat doesn't go away? Why does it
Because
remain in
of
the circular path?
centripetal.
Okay, because of centripetal force. Because, can you tell me in a different way? Yes, yes, try. Why the cat doesn't leave the circle? Because this is a string, right? That string, we are pulling the cat actually, right? We're pulling it, not straight, but in some way we are pulling it towards the center, right? That's why it does not go away, okay? Because we're pulling the cat towards the center of this whole path, right? That's why I'm saying that the cat will not go away because we are pulling it towards the center, okay? Same thing happens here also, right? Do you agree with me? This satellite goes away or doesn't go away? Or just rotates? It rotates, it doesn't go away, right? So I will say there's a centripetal force acting. And if you ask me why there is a centripetal force, my answer will be very simple. The centripetal force is because of gravitational force. The gravitational force also pulls the mass towards the center, okay? But why is the mass not going to the center? Because this mass right now has some velocity in this direction. Same like your cat, okay? If the cat has some velocity in this direction, though you're pulling it to the center, it will not come towards you, right? Because the cat has a tendency of going away also, but it does not go away also, okay? As a result, it maintains a circular path, some definite radius, and stays there, okay? So that's why I'm telling you again here right now, why does this satellite doesn't go away from Earth? Because Earth is pulling it. Earth is pulling it with a force, which is a gravitational force. So I'm going to write the gravitational force between the Earth and this satellite. So I'm going to write that. The formula will be capital G, mass of the Earth, mass of the satellite divided by distance between them, and I have to square the distance between them, okay? The distance between them is not RE, but it is RE plus H. That's the distance between the satellite and the Earth. And I'm going to square it, right? So this is the gravitational force acting between the Earth and the satellite. And I told you just now, what does this force do? This force is the reason behind the centripetal force. There is no actual string attached here. There's no string between Earth and the satellite, okay? The string that I'm talking about is the force, and that force is your gravitational force, and that force gives rise to rotation, right? So if I ask you why there's a rotational force, why we observe a rotational force on the satellite, your answer is because there is gravitational force. Example, if the gravitational force is 100 newtons, it's like I'm saying there's a centripetal force of 100 newtons, centripetal, directed towards the center, okay, which is causing the rotation of this whole satellite, okay. That's why check what am I going to write. See, there's a centripetal force acting on the satellite, and it is because of gravitational force, okay. Let me write now this, okay. I will write the left hand side also. Let me write the right hand side first. Capital G, mass of the Earth, mass of the satellite divided by distance between them. Again, I'm writing RE plus H and whole thing square. Let me write the formula for centripetal force. Okay, maybe I've not done centripetal force at all properly with you all, but actually I may have not done at all. But I'm still going to write today the formula, okay, and I'm going to talk about how to use it. See, let's apply for a cat first. If I want to cat to rotate in a radius, let's say small r, mass of the cat is m, and the velocity with which I want the cat to rotate is v, okay? Then this amount of centripetal force that must act on the cat is given by mv square by r. I'm repeating again, okay? If you want the cat to rotate, the cat should experience centripetal force. How much centripetal force? Equal to this value. And what does it mean? I want the cat to rotate. I must write here the mass of the cat. Okay, the cat wants to rotate. I must write here mass of the cat. If it is 10 kg, you write 10 kg. If you want the cat to rotate with a velocity of 100 meters per second, you write here 100 meters per second. If you want the cat to rotate, or any object you want to rotate, you should write here the radius of rotation. Let me give you, okay, example, 10 kg cat. You want it to rotate with a velocity of 10 meter per second. You write here like that, square that velocity divided by radius. You want the radius to be 10 meters, suppose. So you just write 10 meters. Automatically you'll see 10 and 10 will get cancelled. You're going to get here 100. Okay, that 100 is going to be 100 newtons, by the way, because when you adjust the units, you're going to get newtons. Okay, so what I'm trying to tell you right now is this. See, if you want an object of 10 kg mass rotate with a velocity of 10 meters per second in a radius of 10 meters, then the centripetal force that should act on the object must be how much? Must be 100 newtons. That is how you are going to apply this formula right now. Okay, so I'm going to apply this right now and you tell me whether you're okay or not. Okay, see. So in place of centripetal force, I'm going to write m, which is the mass of the satellite, because we want the satellite to rotate, not the earth. Okay, so it is the mass of the satellite, velocity with which you want the satellite to rotate, divided by the distance between the earth and the satellite, the radius of the rotation of the satellite, right? The radius of rotation of the satellite is this much. See, from here to here, that is re plus h. Okay, so I'm going to write here re plus h, that's the radius of rotation for the satellite, equals to this thing here, capital G MEM by re plus h whole thing square. If the gravitational force is equal to centripetal force, then only the object you will find it is rotating, right? That's why I'm making it equal. Okay, so that's why I'm making it equal. Check what goes cancel. Okay, so the m gets cancelled with this m. This is re plus h, this is re plus square, so I'm going to get the square cancelled. I'm simply going to get v square, velocity square, is equal to capital G M E, mass of the earth, divided by re plus h right now. Okay, so this is the formula I'm getting right now for velocity square. So when I solve it, okay, or let's say when I write it for only velocity, it's going to look like square root of capital G M E divided by R E plus H. Let me tell you how you are going to use this formula. First of all, of course, if you know what is the mass of the earth, if you know what is the radius of the earth, if you know at what height the satellite is present, it means that you can find what will be the velocity of that satellite. This is the formula for orbital velocity, or let's say velocity or orbital speed. Are you clear, guys, how to use this one? If you tell me the satellite is at a height of 100 kilometers, okay, if the satellite is at a height of 100 kilometers, then we can use this formula, and I should be able to tell you what will be the speed of the satellite at a height of 100 kilometers. I hope you understand what I'm saying. Is it okay what I did just now? Is it okay for all? I'm going to wait for some response very quickly. Please, yes, yes. For Jaden is clear. What about others, guys? Yes, yes, Alia.
The question.
My question is, are you clear with what we have done just now? Means, are you clear what I've calculated just now? And how does it depend on height? Right, guys? Is it okay? Shelby is clear with this, what I did just now.
Yes, sir.
Okay, Fiona is here. Fiona. Jaden
Yes.
has already responded. Okay, Fiona said okay. Jaden is also here. Okay, Siddharth is also saying okay, I think. Then who else should I ask? Dasanba is also here. Dasanba is okay. Azrael is okay. It's fine. Whatever I did just now. Azrael. Where is
Yes,
he?
sir.
Okay, for Azrael is also fine. Okay, then okay, then I'll just proceed. Okay, so see now. So let me just ask you this question now. Okay, what will happen if the satellite is not very close? If it is very far, will it move faster or slower? Please look at this formula and tell me. If the satellite is not near, it is very far.
So,
It will slower. Very good. Okay, because if the satellite is very far, the height of the satellite will be very large because it is very far. Since the height of the satellite will be very far, you will see, right, v is inversely dependent on your velocity. Sorry, v is inversely dependent on your height. That means your v is going to decrease. Okay. Anybody who can think logically? This is the Earth. This is satellite number 1, and this is satellite number 2. They are both moving. Okay. They have same mass. Let's say. Why this satellite is going to move slower? Why it is going to move slower, and why this satellite will move faster? Of course, because of the formula. Don't tell me directly because of
due
the
to the
formula. Okay.
acceleration of the
Very good, very good. Because see, this satellite is very close. It is going to experience more gravitational force. Indirectly, it is going to experience more centripetal force. But this satellite is very far. It is going to experience less gravitational force, and it is going to experience less centripetal force. That's why this satellite is going to run slower and this is going to run faster. Okay, I hope you understand what I said just now, guys. Okay, I hope you understood that. Okay, so let's proceed now, and let me just show you what else can I do with this formula. Okay, so there's a much better way to write it down. I'll just show you now. Just now you have learned orbital speed is equal to how much? Root over of capital G ME divided by RE plus H. You have to remember this because it will be handy, okay? Okay, now see, I just want to change the form, the way it looks, okay? So just check. All of you will agree if I write small g, which is the acceleration due to gravity on the surface of the earth, right? The formula is capital G. I have to write mass of the earth and I have to write radius of the earth square. Okay, we have done this only in the previous classes. Okay, so I'm going to use this formula right now. Check. Okay, so I'm going to write in place of writing like that, I'm going to write GRE square. Everybody knows G is 9.8. Approximately, we take it like that, equals to capital GME, right? So I can do that. Say, in place of writing GME, I can write GRE square. That is what exactly I'm going to do in this formula right now. Okay. So orbital speed will be equal to root over of small g capital RE square divided by RE plus H. RE plus H. Okay. So this is what we have got just now. See, this is the formula again, not in terms of capital G and mass of the earth, but in terms of acceleration due to gravity and radius of the earth. I hope you understand what is the change. Okay. Let me make one more change and then I will speak about this. Everything is inside the root. Okay. So now see, if I tell you that height of the satellite is very small, H is small means the satellite is very far or very close. The satellite is very close to the surface of the earth. Close to surface of earth. That means the value of H is small, no? Maybe only 100, maybe only 10 kilometers, 20 kilometers, or 30 or 40 or 70 kilometers. No, that means, let's say 400 kilometers. Very small height, okay? Now, radius of the earth is very big, okay? Radius of the earth is how much? 6.4, if you remember, 10 to the power 6 meters, no? If I can convert into kilometers, it will be still 6,400 kilometers, around this much, okay? So it's a very big kilometer. See, radius of the earth is very big, okay? Just now I told you, if I put this approximation, I'm just applying this now. If I tell you the height of the satellite is very, very small, then you can have a much simpler formula. See, I can write V equals to root over of small g, RE squared divided by simply RE. I'm not writing H anymore. See, why did I not write H? Because you are writing RE plus H, and I'm telling you that the satellite is very, very close. That means H value is very, very small. H value is so small that I can neglect it and no need to add with RE. It's like 6,400 kilometers plus only 10 kilometers, right? So you can neglect this 10 kilometers, okay? Because let's say 100 kilometers. So you can just neglect that. Why? Because height of the satellite is very small, no? So I've just removed H, okay? So see, from this formula, I've removed H, and when I do that, this RE and this will cancel, and I will write V equal to root over of just G and RE. So let me ask you, please tell me, guys, what is this? If you can tell me what is this, I'll be very happy. What is this? Is it the orbital velocity of the satellite or not? Yes, it is the orbital velocity of the satellite. When? What is happening? In every case, or when the satellite is very close to the earth? Whenever the satellite is very close to the earth, you can use this formula directly. Okay, and I can even tell you what is the value. See, because I'm going to write velocity is equal to root over of G is 9.8, so I'm writing 9.8 into radius of the earth is 6.4 into 10 to the power plus 6 meters. I'm writing SI units. I'm going to get some value here. Okay, let me tell you how much we are going to get. I'm going to get 792 0 meters per second. That is like writing 7.92 kilometer per second. Just imagine, okay? So what do you think? It's a speed of very high speed. Imagine a satellite very close to the surface of the earth where the height is negligible, right? The approximate velocity of the satellite will be 7.92 kilometers per second. It simply means this is earth. You have a satellite very close to the surface of the earth and you want the satellite to rotate, no, around the earth. So it must have some velocity to rotate, right, around the earth, no? That velocity is how much? Around 7.92 kilometers per second. Obviously, if I take a satellite higher and higher height, you will notice the speed of the satellite will become smaller and smaller. Okay, so that is what we have discussed just now. Okay, guys. So guys, are you okay with this one? Just now what we have done. If you say okay, I will proceed.
No, sir. So could
No,
you please repeat the height portion?
height portion. Which part? From where? From which height part? Are you clear that I'm talking
So
right
how
now?
did you remove the height?
Oh, how did I remove the height? Okay, let me ask you like this. Okay, see. This is Earth. Okay, this is Earth, no? What is the radius of Earth? 6,400 kilometers. Okay. Then I'm telling you, suppose, okay, not every time, but suppose, no, one of the case, no? If the satellite is very close, what will be the height of the satellite? What do you think? Will it be 6,400 kilometers? No, right? It is not going to be so big. Okay, it's going to be very, very less. Example, height can be around 100 kilometers. Just an example. Okay, let's say only 50 kilometers. Just an example. Okay, it's a small height. So if I'm asking you, what is RE plus H, right? You are going to tell me, yeah, RE plus H is 6,400 plus 50 kilometers, right? Can I tell you just that, okay, let's just ignore this, right? 50, because we are adding 50 to a very large number. We can approximately say that we can just remove this small height, no? And no need to add with radius. Can you understand?
Yes, sir. Yes, sir.
When you add a very small number, x plus y, I tell you x is very large and y is very small, right? So when I say that x is very large and y is very small, the answer is almost equal to x, right? The bigger number. Approximately, of course, okay. I think you got the point now, no, I think?
So can you explain this
Yes,
part
sir.
again?
Which part again? This, how do I remove the height? How did I remove the height? Is that your question? Latifa, Latifa? Okay, so see, I told you just now, I told you, suppose if I take a satellite very close to the surface of Earth, not every time you cannot come and remove the height, okay? The formula is this, see, the formula is this. The formula is this, okay, sorry, this one. This is the formula, yes, this is the formula, and this is the formula. You cannot remove the height at all, you have to put the height, okay? But if I tell you, the height is small, under this case, when the height is very, very small, compared to, of course, radius. No, that means the satellite is not very far, okay, very close to the surface of the Earth. It's like writing RE plus H, and I'm telling you that height is small compared to this radius. Radius is very large and height is small, okay. In that case, I can say this is almost equal to the radius, right? Because it's like writing 6,400 plus only 50 kilometer, which is the height of the satellite, okay, or maybe 100 kilometers, no? So instead of writing this 50, I can just ignore, I'm still going to get 6,400, close to this number, right? Adding a small number to a very big number, the result is a very big number, right? Close to the big number, right? So if I write x plus y, okay, if I write x plus y and I tell you y is very small and x is very large, what's your answer? Your answer must be x. Even this also is true, say x minus y. I tell you this is like 1 million and this is like only 1 or 10. What is your answer? I'm subtracting 1 million and 10. What is your answer? Will you get the answer close to this small number or close to this big number? Yeah,
Close to
removing
the big number.
big number, yeah, because you are removing a very small number, very tiny number from a big number. You are going to get a big number that is like x only, right? So we can do that, okay? We can approximate x plus y equal to x and x minus y also equal to x. If y is very small compared to x, we can do that, okay? So that is what I've done just now. I think you got it right now. Is it okay? Can I proceed?
Yes, sir.
Okay. So now see, okay. The next thing I'm going to show you that we are going to calculate now, okay? How much time a satellite takes for it to rotate around the Earth. That is what we are going to do next, okay? So keep a track of the formulas, okay? So let me just tell you what we have got. The velocity with which a satellite is rotating, right? Of course, if we know the height, then only we can calculate. We have done that just now and we got a formula. So I'm going to write that formula. If you remember, let me just remind you. It was root over of capital G ME, if you remember, divided by RE plus H. Another way to write, I showed you just now, is equal to how much? Root over of GRE. I have to square it divided by RE plus H. Only under height is very, very small, then the formula for V becomes how much? Root over of just simply GRE. Okay, because your H is very small, I can neglect this H. RE square and RE gets cancelled, so you just get GRE. This is when H is small. Okay, this is what we have done just now. Okay, so I'm going to proceed now. See, guys. So this is the mass of this satellite. This is the satellite I'm talking about, still orbiting in this orbit with a velocity which we have found just now. The expression for velocity we have found. Okay, we know how much is the velocity at what height. Okay, now we are going to find out how much time it takes for the satellite to make this one round, one circle. Okay, To find the time, right, we call it this time, that time taken by the satellite to complete one rotation, we call it time period. We are going to use this formula. See, if we know velocity, we write velocity is distance by time, or speed actually. Speed is distance by time. I'm using the words velocity and speed same, okay? It doesn't matter right now, okay? So I might say velocity, it means speed, speed means velocity right now. So the velocity of the satellite will be how much? Distance or displacement by time, distance, let's say. Or I can also write time, right? Time can be written as distance by velocity. So I'm going to do that, see. So I'm going to write here some distance, and I'm going to write divide by velocity or the speed. Okay, now you guys tell me, okay, see. This capital T is a very specific time. It's the time taken to cover one round. In one round, how much distance the satellite has to cover, guys? Can I say it is the circumference or not of this circle that I have? In a time of capital T, we have to go one round. Going one round means the satellite has to cover one round. One round means circumference. The circumference will be 2 pi times radius of this big circle, okay? The circle has a radius of how much? Re plus h. So are you guys okay? I've written here circumference. That's the distance it has to cover, right, in one round. Because we are calculating the time covered in one round, okay? Divide by with what speed it is doing? It is doing with a speed of v, right, which we have already calculated. I'm going to just use the formula now, okay? Guys, are you okay with this one? Just check. I hope you understand the meaning of what is what. That's it. I think everybody understands what is capital T, no? I think I can proceed. Okay, then I'm going to proceed, okay?
Yes, sir.
Yeah, so I'm simply going to use this formula now, okay? Let me tell you, I'm going to use this formula now. See, this one. This one, okay? Of your V, no? I'm going to use that, okay? So check, and you can help me out. So I'm writing like this. I'm writing here T equals to 2 pi Re plus H. I'm going to divide by V, and V just now you saw it is root over of capital G M E divided by Re plus H. No square, nothing, okay? So we got this one. We're going to arrange now, okay? Check. When I arrange, everything is going to look like this. Not everything. Let's arrange slowly. So I get 2 pi here. Then in place of this R is Re plus H. Okay, this one, numerator one, this one. I think you will agree if I can write like this or not. Check. Can I write like this? Check. Instead of this, can I write like that or not? Just check. Same, right? This root and this square will get cancelled. I still get Re plus H. Okay, so I just want to write that square root and square also. I think we can do that, right? Okay, so let me just write it down. Okay, and you tell me whether it's okay or not. See, in place of REH, I want to write Re plus H, but I want to give a square also so that they get cancelled, and I'm having the same thing. Okay, divided by, of course, the same thing that I have, but let me just arrange it. Let me just write here GM because it is dividing by GME. This one, which is in the third level, will go to the first level. Okay, so it will go as root over of Re plus H. I think you understand the steps. Just check.
Yes, sir.
Okay. Latifa has said yes. What about others? If you're okay, then I'll proceed. One more response, please. Of course,
Yes,
if
sir.
you're not understanding, you can tell me. Huh? Okay, okay. Then you can stop me. Huh? If you're not understanding, say. So you know what I can do now? I can say this also has root. I can say this also has root, and both are okay. Actually, I can write everything whole root. See, whole thing root. Re plus H square, and then we have Re plus H because everything has root divided by GME, right? That also has root. No, so I'm putting a single root right now. Okay, so that is what we have. From here, I can simply write twice pi root over of Re plus H whole thing cube now, cube divided by GME. So this is one of the way to write this formula, okay? And there's one more way, I'll just quickly show you. As you can see, I can also write like that. Then this Re plus H, I can do that. Cube here divided by GME, right? In place of GME, you know, right? We can write GRE square if you remember this. Because I showed you G is equal to capital GME by RE and square. So in place of GRE, right, I can write GME, or GME can be replaced by GRE square. Okay, so I'm doing that right now. You can see. So either I write that or I write like this. Okay, it doesn't matter. Okay, but the point is this. You tell me, which kind of satellite will take more time? The satellite with smaller height or more height? The satellites which are closer to the Earth or satellites which are farther from the Earth? Which kind of satellites will take more time? From this formula, what do you learn?
Yes, sir.
Yeah, which are further, right? H means height of the satellite. If the satellite is going far and far and far, okay, the time taken up by the satellite will be more, right? And that is why it's very obvious. See, okay, let's compare. Okay, very quickly. This is Earth. I'll ask you the reason, of course. So if I have a satellite in this orbit, a small orbit, satellite number one, then if I have this satellite, okay, in the bigger orbit, satellite number two in a much bigger orbit, okay. So obviously by now you will tell me, ah, this satellite is moving faster. Okay, this is faster. This satellite is moving slower. Look at the number one and number two satellite, okay. First satellite is moving faster and it is going to cover less distance also, right? So it will take very less time to cover one round. Okay. What about this one? It is moving slower also because it is very far. And it has to cover a lot of circumference also, right? So obviously, number two satellite, what do you think? It will take more time. Okay. That's why you can understand more height means the satellite is going to take more time. I hope you got my point. Okay. I think it's okay, right, guys?
Yes, sir.
Okay. Then
Yes, sir.
okay, I think yeah, that part is clear. Okay, fine. So I'll just show you one more thing of how to arrange all of it, and that's a very nice way again. Okay, just I'm showing you because sometimes there's a question on this. Okay, so very quickly I'm going to do that. I told you last time, if you remember, density is equal to mass by volume. I can replace the mass by writing density into volume. I can do that. I can replace the mass. Okay, so see, if I want to replace mass of the Earth, I have to write density of the Earth and I have to write volume of the Earth. Not velocity of the Earth, but volume, okay? Volume of the Earth. I think you got me what I'm trying to say. So volume, okay? Volume of Earth. So mass of the Earth can be replaced by density of the Earth. Volume of the Earth, it's a sphere, no? So volume will be 4 by 3 pi r cube. So this mass, I'm going to put over here, check. I'm going to put over here. And when I do that, let me show you what we are going to get, okay? Just copy it, paste it. Give me 1 second, guys. Okay, so let's do it slowly. Let's not be in a hurry. So let me just remove the mass now. I told you just now, mass will be replaced by density and then volume. So volume is 4 by 3 pi re cube. So let me tell you when we will use this. You are going to use this if the question says they have given the density but not the mass. I'm repeating again. If they give you the mass, of course you use this formula. No problem. We'll use this and we should know the height. And of course, if you know the height, I can tell you the time period, no time taken by the satellite. Okay. If you don't tell me the height, I will not be able to tell you the time period of the satellite. Please remember that. Okay. So I need to know the height, no? Then, and of course, you have to tell me the mass to use this formula. Okay. But suppose I tell you that I tell you the height, I tell you the radius, but I don't tell you the mass, but I tell you the density. Then in that case, you have to use this formula. Okay. Check these things are in the notes. Those who have not collected the notes, I can send you the picture again today also. Okay. Please revise it today only. Huh? So I'll not proceed right now. Not proceed means I will proceed right now. I'll not talk about this much more right now. I think you are okay with this. Okay. When we do the numericals, everything will be fine. Okay. Now check. See. Let's go to the next one. Okay. The last topic is height of the satellite. For that, I'm going to just use this formula only, and then from here we'll proceed. Okay. There's a catch here. Okay. I just cannot find the height of the satellite. I will do something and then I'll tell you what is going on. Okay. So just check. See. The last thing I want to talk about is what will be the formula to calculate height of the satellite. Suppose we don't know what is the height of the satellite. Okay. So let me just show you. Let me go back and here. See. Where am I? Here, no? Give me 1 second. Okay. You will understand what I'm trying to say. Oh, I went too much up. Yes. This one, see. Can I tell you from this formula? If I tell you what is the speed of the satellite, I'm repeating again. If I tell you what is the speed of that satellite, you can arrange the terms and get the height of the satellite or not? Yes or no?
Yes, sir.
Okay, so this formula reversely can give me height also. Okay, but of course I have to arrange the terms and all. If I tell you how fast that satellite is moving, right, around the Earth, I should be able to tell you what is the height of the satellite. Okay, so this is quite obvious and quite simple, common sense, of course. Let's go back here now. Okay, In this one, I will show you that if you tell me the time period of the satellite, I should be able to tell you height of the satellite. Suppose I tell you the satellite takes 30 days. Okay, just an example, 30 days to go one round. That means I'm telling you the time period, no? So I should be able to tell you, okay, because of this formula, after arranging, right, I should be able to tell you what must be the height of the satellite. That is what is going on, okay? So at a fixed height, you will have a fixed time period. At a fixed time period, we'll have fixed height. So that's why we can use this right now, okay? So just check. I want to isolate height and get the height, okay? For that, I'm going to square both sides because I need to remove the root. Otherwise, I'll not be able to write h equals to how much, right? So I'm going to remove the root, okay? To remove the root, I'm going to square both sides. When I square both sides, I'm going to get t square equals to, I'll get 4 because of 2, I'm going to get 4. Pi will be, I'm getting as pi square, and this whole root will be gone. So I'm going to get re plus h whole thing cube, and then I'm going to get gme, okay? So I'm going to get this. Let me just do on this now, work on this now, then I think things will be fine, okay? So let me just do that. So see now, I'm going to write t square. I'm going to write capital G M E because you can understand this I've taken on the left hand side. Divided by this, I'm going to bring on the left hand side again. So 4 pi square equals to RE plus H. I'm slowly trying to isolate your H. Okay, so this is the step. If you're not understanding, you can stop me, huh? Okay, the next step, see. I want to remove this cube, right? Cube. So in order to do that, I'm going to put GME t square by 4 pi square, no change in that. I'm going to keep everything power 1/3 on the left hand side, and even on the right hand side, right? If I give a power of 1/3 on the left hand side, I must give also a power of 1/3 on the right hand side. I hope you understand. Check. Why did I do that? Because this 3 and 3, right, will get cancelled, and I'm simply going to get RE plus H. I hope you understand this step. Just check, guys, if it's okay or not. Or I can tell you directly also. Okay, I can tell you directly also. If I'm shifting this power 3 on the other side, it becomes cube root. So this is going to look like cube root actually. I hope you got me what I'm trying to say. Okay. So let me just write it 1/3 only. It means cube root only, right? Power half, no? X to the power half means what? It means square root of x. X to the power 1/3 means what? It is like cube root of x. Okay. So we are dealing with the same thing. Okay. So don't worry about that. But you can understand now. This will get cancelled with this. So once we cancel them, I'm simply going to get RE plus H. You can check it's equal to GME t square divided by 4 pi square and whole thing to the power 1/3. Okay, so this is what I've written just now. See, okay. Now finally, I'm going to write H. H will be equal to this thing again, capital G M E t square by 4 pi square whole thing to the power 1/3 minus RE. This is how you are going to calculate the height of the satellite, provided I tell you what is the time period of that satellite. Okay, I think you got my point. I think it's okay. I think I can proceed. You just have to check the steps. That's it. Did I make it clear? Can I proceed, guys? And one more thing. Okay. The GME, right? As I told you, you can always replace it by GRE square. They tell you the acceleration due to gravity. They tell you the radius. They don't tell you the mass. Don't write GME there, right? GRE square. No, that is the point. Okay. I hope you got my point. Okay. So, and any doubts still share? Because I'm going to tell you now very big thing. Okay. Big thing means very important thing now. Let's revise the formulas. Okay. Anything you want to ask before I proceed? I'm going to wait for 5 seconds, 6 seconds, like that. If you have doubts, you can stop me. Ask anything you want to ask. The steps, of course, right now you cannot remember. You have to practice. Huh? Physics has become like maths. Okay, not like class 10 anymore. No, you have to practice. If you don't practice, go on. See. If you don't practice, you get 0. Okay, so it's like that now. Okay. So let's just quickly revise. Okay, I don't know how much you remember. Let's revise. Okay, let's revise the formula for your V. The formula for V is root over of capital GME divided by RE plus H. Also can be written as GRE square here inside the root. I'm writing. You can take it out also if you want. Let's still write RE plus H. You know a special case where height is very small. You can neglect the height and you know how does it look like. Then the formula for time period, if you know the height, okay, the formula for time period was like this, say 2 pi divided by RE root over RE plus H, whole thing cube, if you remember, divided by G. Then I've talked whatever I need to talk. I've talked about that. Finally, we got H equals to, okay. H equals to, we got T square. Let me write capital G M E, if you remember, divided by 4 pi square, 4 pi square. This GME, I told you I can replace by GRE square anytime I want, and the power was 1/3 minus RE. Okay, so this is the formula, the three formulas we got. Now I'm going to tell you the big thing. See, so we know with what velocity a satellite is moving, with what time period of the satellite is, and what is the height. We can do calculations on that. Okay, now I'm going to tell you a big thing. See, okay, and you can do this anytime you want. This is Earth. This is the satellite I was talking about. One second, one second. Okay. This is the satellite I was talking about at the height of H from the surface of the Earth. Where is the rest of it? Not visible. Okay, now it's visible. Okay, now see. Be with me, you will understand what I'm doing. Okay. So suppose I tell you this is Earth and these are the calculations, right? I've kept the calculations also. Okay. Suppose I tell you this is not Earth. Suppose I tell you this is Jupiter. And this is a satellite rotating about Jupiter. And this is of course not the radius of the Earth. This is the radius of Jupiter. Okay. RJ, let me call it RJ, radius of Jupiter. Okay. And this H is not height of Jupiter. Okay. This is the height of satellite again. But of course, this satellite is moving around Jupiter now. Okay. So with some orbital velocity, with some time period, this satellite also will have some time period, no? Now you tell me, guys. Okay. Will the formula be different or formula will be exactly the same? Or there will be changes? Will I write capital G and mass of Earth, or I have to write now mass of Jupiter? What do you think?
Mass of Jupiter, sir.
Mass of Jupiter. The velocity of the satellite depends on mass of Jupiter. Please remember that. Don't write mass of satellite there, okay? And of course here I will write radius of Earth or write radius of Jupiter now. Radius of Jupiter. So can you understand? I'm using the same formula, no change at all. Just that the mass of Jupiter and radius of Jupiter, right, in proper places are kept. Can you understand how I am changing the formulas?
Don't we need
Yes,
to
yes.
remove small g of
Yes. Very good. Tell me something you have asked. Are you asking? Yes.
do we need to remove small g also?
Small g. Yes, of course. You tell me what is small g? Acceleration due to gravity on the surface of the Earth. What do you think I will replace it by? Acceleration due to gravity on the surface of Jupiter, which may not be 9.8. It will be something different, right? So I'm going to call it small g, but write j there. That means acceleration due to gravity on the surface of Jupiter. I think you got me right.
Yes, sir.
Okay, what about small g formula? It will be what? Capital G, okay, no problem. Mass of Jupiter divided by radius of Jupiter whole thing squared. Not whole thing, but radius of Jupiter squared. This is how I'm going to write, see. This is how you calculate acceleration due to gravity on the surface of Jupiter, okay? Exactly the same form as you got on Earth, okay? And of course, here also I have to make changes. This is not Earth anymore. This is Jupiter and this is plus. Okay, let's go to time period. Time period also, right? It will be radius of Jupiter. So you just have to remember one formula actually, okay? Just remember for radius of, just remember for Earth, and then you can do it for any planet that you want, like that, see. Okay, here also, height of the satellite. So this will be time period of the, not Jupiter, okay? Don't write time period of Jupiter. It's the time period of the satellite. Mass of Jupiter here, of course. 4 pi square in Jupiter and Earth is same, so don't change anything there. Don't write 4 pi in Jupiter, don't do that, okay? And then we have RJ. So I think you understand, right, this one? All of you is clear with this one. All of you are clear. I'll show you one more change, okay? Very quickly. I'll do that if you are clear with this one. Yes, guys. Yes. Hurry up. Yes.
Clear, sir.
Clear. Okay, fine. I'll do one more change. Now check. Why is the satellite rotating around Jupiter or Earth? It's because of gravitational force between Jupiter and this satellite or the Earth and the satellite, no? Now check, okay. If I bring, you're confused what I'm bringing, no? This is Sun, 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 okay? You know Sun. Sun will also have some radius, yes, radius of the Sun, no problem with that. Who's rotating around the Sun, tell me? Satellites are rotating around the
Jupiter,
Sun or
sir.
planets? Only Jupiter or all the planets?
Planets.
Sir.
All the planets.
All the
This is
planets.
all the planets. This is a planet. Okay, let it be any planet, Earth, Mars, Jupiter, anything. Okay. Now you have to start treating the planet like a satellite. Can you understand? It is looking like the same picture or not? Check.
Yes, sir.
Same picture, right? Okay. So if I ask you, is the planet rotating around the sun in some orbit? Yes,
Yes,
it will
sir.
rotate with certain velocity. We will call it what velocity, guys? Orbital velocity of the planet. This is not called height of the planet, but let's say this overall we can call it what? Distance of the planet, no? RS plus H. RS plus H is what? Distance of the planet from the sun. H, of course, I can tell you is the distance from the surface of the sun to the planet. Okay, so I can do that. We can use it like that. Again, this planet will go around the sun, right? Yes or no? The planet will go around the sun. So I can use the same formulas. Okay, but of course, what will be the change now? If I'm calculating the velocity of the planet, I have to write here mass of the sun. If I'm writing the time period of the planet, I have to write here radius of the sun, acceleration due to gravity on the sun, which I will not do. I will write GME only, mass of the sun. I will use, okay. Here also height of the planet means I have to replace here mass of the sun, and this is the radius of the sun, okay. But I think you got my point, how to use this, right? Okay. Now I'm going to ask a simple question, okay. Tell me, what do we know about Earth and Sun? Suppose this is Sun and this is Earth. Let me ask you directly. Do you know what velocity is this Earth rotating around the Sun? Do you know or you do not know? Now tell me, be frank, be frank. It's not about feeling shy, okay? Not knowing, okay? Just say you don't know, right? Or anybody knows? We don't know right now, right? We do not know, okay? Do I know the time period of the Earth around the Sun? Do I know how much time it takes for the Earth to go one round and come back here again? Do I know this?
Yes, sir.
Yes, very good. We know this, yes. And we don't have to take a watch for this, right? We know this. How much is the value?
365 days.
Very good. 365 days. Do you all agree with me? Since we know the time period, okay, since we know the time period, since we know the time period, let's come back here. Can I tell you I can find how far is Earth from the Sun or not by calculating this H? Indirectly, I'm telling you that, or by using this formula. Because I'm going to put here 365 days converted into SI units, no problem with that. But time I'm going to put, of course, I have to know the mass of the sun and all, okay? So mass of the sun and all these things. But I think you understand, right? So can I say it's an indirect method, right? Indirectly, we are trying to calculate what is the H between Earth and Sun, no H, okay? We can do that because we know this T already is 365 days, okay? We can also indirectly, right? I can tell you now, we can even calculate your V, the velocity of Earth, average velocity, of course, with which the Earth is rotating around the Sun. I can do that for any planet. Okay, that is what I'm trying to say. And finally, I can also, I already told you what is the H value. Okay, so I think you got my point, how to apply these formulas. Okay, so what I will do right now is that for today, I will stop, but I will give you, let me see, where is that book? Okay, I will try to do like this. I will find out, I'll send you the notes right now only, and I will give you questions right now only, okay? It's been so many days, I'm not making you work much, okay? So I think you have become lazy, but today I'm going to do that, okay? So today I'm going to send you some questions right now only, guys, okay? So whatever I've done just now, I'll send you the pictures. Please revise them right now only, and start solving. If you have time, you do it right now only, okay, guys? Is it okay? Is it okay? Or you are lazy? Very lazy. Is it okay, guys? I don't want to touch anything new right now. Okay, let's go slow, but let's go properly, no? So let's finish numericals based on these three formulas that I've given you today. Okay, so I'll do that. Okay, so bye bye, guys. Huh? For today, I'm stopping. Huh? Yes, yes. If it's okay, if nobody has question,
Yes,
then I'll stop. Okay, okay. You are saying okay, but anybody who wants to ask anything, I'm here. Otherwise, you can slowly leave. Huh? Yes, yes. I'm still waiting for some questions, some doubts. Still waiting. Otherwise, you can leave, guys. I'm not going to be angry, of course. If you don't have doubts, you can leave. If anybody has doubts, you want to ask anything, I'm still here. Okay. Azriel has left. He's fine. Don't worry, I'm not going to keep checking your name, okay? Who's leaving and all. Okay, nobody's asking me anything. Okay, bye. I'll not bore you, okay? Bye. Huh, guys? Bye. Good.
Thank you, sir.
Uh,